Welcome to the 7th lecture in this series on tensor analysis. Let me begin this lecture with an apology. At the end of the last lecture, I had promised that from the next one, that is, from this one, we are going to start talking about 4 vectors, 4 covectors, and other things which are useful for the special theory of relativity. And then we are going to go on to talk about general vectors, tensors, and such like objects under nonlinear transformations, which would be useful in general relativity. I'm not going back on that promise. I'm just delaying the delivery of those lectures a bit, given the fact that we are going to switch from the basic structural aspects of the subject that we have been discussing so far to more practical, calculation-oriented stuff. In the next part of this series, what I want to do in today's lecture is sort of take a look back at the issues that we have covered, but from a different point of view. We would essentially be asking in this lecture one question, and that question is, why tensors? Come to think about it, this is really 2 questions rather than 1. Firstly, why do tensors exist? And secondly, why do we need them? I'm going to try to answer both of these questions today, although we have seen answers to these questions, at least partial answers to these questions, in previous lectures as well. In addition to this question, why do they exist? There is a supplementary question. Could something else exist? Something other than tensors? Now, this is a huge, big question, and the answer is not that simple. So what we will do to begin with is we will focus on a special kind of tensorial object, which is more familiar to all of us and which is also something which will give us enough details to begin our journey towards understanding this. I am talking about tensorial objects under rotations. So ordinary 3-dimensional objects which transform in a particular manner under rotations. So we will begin by some questions. And these questions may seem rather trivial at first, but you will realize that they are actually quite deep. So the first question is, and remember, all of these questions are in the context of rotations and ordinary 3-dimensional space. So the first question, have you ever heard of a single component object, that is an object which can be described by one single number, that is not a scalar? 2. Do you know of any object in 3 dimensions that is described by precisely 2 components? Now, the cleverer among you might immediately come up with an answer to this one. You might say, why? Just take 2 scalars. They are described by 2 numbers and they are well-defined objects in 3 dimensions. You would be right, but that's not the kind of object that I'm talking about. This kind of trivially clubbing together lower rank objects to try to build bigger ones is not what we are talking about. Do you have something for which you intrinsically need 2 numbers? Something from classical physics which is of this kind? Think about it. I am pretty sure that for most of you the answer will be no. Of course, another possible answer could be a vector in 2D. However, let me point out that we are not talking about 2-dimensional space here. We are talking about objects which exist in all of 3 dimensions. So even if a vector had only 2 components to begin with, if you were to rotate your coordinate system so that the coordinate planes change, then this object which had only 2 components would end up having 3 components. So this is really a 3-component object, not really a 2-component one, unless you are dealing with a world which has 2 dimensions only. But that is not the kind of thing I'm asking about here. There could be many more questions, but finally one more question. Do you know of anything that can be described by precisely 3 components, 3 numbers, not 3 scalars? leave that aside, which is not a vector, which is something different. Now, if you have gone through my previous lectures in this series, you might immediately come up with an answer to this one. You could say, well, covectors in 3D are different from vectors, and they are described by 3 numbers. Or you could say, axial vectors are not really vectors, they behave differently under reflection. They are also described by 3 numbers. Let me point out, however, that we are talking about rotations and rotations only as the kind of transformations we are going to allow for the time being. And as far as rotations are concerned, both covectors and axial vectors transform exactly the same way as vectors. You cannot distinguish between vectors and covectors or vectors and axial vectors if all you were ever interested in were rotations. Indeed, that is one of the major reasons why you hear about covectors or axial vectors rather late in the day. You do not need to distinguish them from vectors as long as the only symmetry operation you are worrying about are rotations. Let us start with a somewhat detailed answer to the first question. Does there exist a single component object, that is not a scalar, under rotations? Let me emphasize that what we are talking about are well-defined objects which are completely described by a single number. In other words, we are not talking about things like the x component of a vector, which of course is a single number. However, if you just knew the x component of a vector in one coordinate frame and nothing else about that vector, then there would be absolutely no way of finding out even the x component of the vector when you rotate your coordinate frame. So such objects are not things that we are talking about. We are demanding that that single number describes the system completely so that you should be able to find out the value or the number describing the object in each and every coordinate system, provided you know its value in one. For scalars, the rule is rather simple. If you know the object in one coordinate system, that is, you know the number which describes the scalar, that number is the same in all coordinate systems. So the question that we are asking here really is there a way in which the number can change from coordinate system to coordinate system when you rotate your coordinates? To address this question, let us take a look at this setup. Even with my poor drawing skills, I'm pretty sure I've been able to do justice to this situation. You have 3 coordinate systems. You start with an original one labeled x, y, z on the left here, and in that coordinate system, the single number which describes our object has a value a. Now we carry out a rotation r1. Our coordinate system changes to x prime, y prime, z prime, and the value as measured in this coordinate system of that number describing my object is a prime. We follow this up with another rotation labeled r2, which takes us to this x double prime, y double prime, z double prime coordinate system, and the number has changed now to a double prime. The question that we are going to investigate here is, what kind of relationship has to be there between a prime and a double prime? Of course, scalars are the simplest in this regard. If this object were a scalar, a double prime would have been the same as a prime, that would have been the same as a. What we are trying to investigate is there some other possibility? And a very, very important point in this whole discussion is going to be this rather mundane fact that instead of rotating the coordinate system, the original one, the one labeled x, y, z, first through r1 and then through r2 to arrive at x double prime, y double prime, z double prime, we could have carried out the same transition from x, y, z to x double prime, y double prime, z double prime by carrying out a single rotation. And this single rotation is the so-called product rotation r2, r1. Remember, when we talk about products of rotations, is the one which you write on the right hand side that acts first. So r1 acts first, then r2 acts, and you are ending up with an overall single rotation, which we could have called r3, for example, which has exactly the same effect as carrying out r1 first, then carrying out r2. This is going to be critically important in what is going to come. Now, let us propose a possible non-scalar behavior. Let's imagine that this number a doubles every time you rotate. So after you carry out R1, a prime becomes twice a. Then you carry out R2, a double prime becomes twice a prime. So after the two rotations in succession, we will end up with a double prime equals 4 times a. However, there is a problem with this, and you may have already spotted that. Instead of rotating in succession through R1 first and then applying R2 after that, we could have done the same thing by rotating once through this rotation R2, R1. And if you had gone to the final coordinate system from the initial one by a single rotation R2, R1, then our rule that the number doubles every time you rotate would have given you a double prime equals 2a. So in this case, what is happening is, if you go from x, y, z to x double prime, y double prime, z double prime, through a succession of two rotations, first R1, then R2, your number is turning out to be 4 times the original number a. If you are going to the same final coordinate system using a single rotation, the number turns out to be twice a. Now, the numbers describing an object can depend on the coordinate system. We know of plenty of examples of things that do. Vector components, for example. However, they depend on the coordinate system and on the object, but not on how you got to that coordinate system. In other words, the history of how you arrived at this coordinate system starting from some initial coordinate system, that should not affect your final answer. And this hypothesized transformation rule that we have talked about, that the number doubles every time you rotate, is simply not consistent with this basic principle, that ultimately your numbers may depend on your coordinate system, but they should not depend on how you got to that coordinate system. And that simply rules out this particular transformation rule, so to speak. That of course does not mean that no other transformation rule is possible, only that this particular one is not. So let us take a look at this at a slightly deeper level. So the rule that says every time you rotate, the single number describing your object gets multiplied by a fixed factor, a factor other than 1, is simply out. That will not work. But what about a factor that depends on the kind of rotation that we are carrying out? And for the time being, let us focus for simplicity on a subclass of rotations. Just rotations about a fixed axis. Let's say the z-axis. So what happens if we have this rule that the factor by which my number gets multiplied is a function of the angle of rotation? So under rz theta, rotation through an angle theta about the z-axis, let's propose that the rule is a goes to lambda of theta times a. And this lambda of theta is a smooth function of theta. Now, for rotations about a single axis, there is a very simple combination rule. Rz theta 1, rz theta 2. That is, rotate about the z-axis through an angle theta 2 first, and then rotate about the same axis through an angle theta 1. Of course, leads to an overall rotation about the z-axis through an angle theta 1 plus theta 2. Rz theta 1 times rz theta 2 is rz theta 1 plus theta 2. Now, if you are going to demand that your final value for the number describing your object will not depend on whether you carried it out in one step, that is, rotated through theta 1 plus theta 2 in one go, or carried it out in two steps, first rotated through theta 2 and then through theta 1, the obvious conclusion would be that this lambda of theta must satisfy lambda of theta 1 plus theta 2 must be equal to lambda theta 1 times lambda theta 2. Now a smooth function that satisfies this is actually pretty well known. All of you should know the identity of the function which satisfies this. It's nothing but the exponential function. Lambda of theta is e to the power alpha theta for any alpha whatsoever. So as long as we stick to rotations around one axis, it seems that it is possible to find a single component object whose number changes when you rotate. The change here would mean multiply by a factor which is given by e to the power alpha theta for a fixed alpha. There is a catch though. If you rotate about the z-axis through an angle 2 pi, 360 degrees, what you get back is your original coordinate system. And that implies that you have to go back to whatever original value your number had. After all, it should not depend on whether you have turned the whole coordinate system around and come back to your original state. The number can depend on the coordinate system, remember, but not on how you got there. So the factor by which you would multiply for such a rotation must be 1. So e to the alpha theta must be equal to 1 when theta is 2 pi. And the only possibility for that, at least for real numbers, is alpha equals 0. And that means that the only possibility that you really have is lambda of theta has to be equal to 1. So scalars, the things which get multiplied by 1, or rather does not change when you rotate your coordinate system, are the only kind of one component objects as long as you're sticking to rotations and rotations only. Please don't come up with the objection that there are pseudoscalers which change sign under reflections. While pseudoscalers do exist, and they are important, they are exactly the same as scalars as far as rotations are concerned. Note that for the time being, we are only talking about objects under rotations. And under rotations, there are only scalars which count among one-dimensional objects. There is no other possible transformation rule. To see what the scenario is for more complicated objects, let us go back to our setting once again. We have this bunch of rotated coordinate systems. X, y, z rotates to x prime, y prime, z prime, then to x double prime, y double prime, z double prime. The only difference is, this time instead of focusing on an object which is described by a single number, we are talking of an object which requires capital N numbers to describe it. A1, A2 all the way up to A capital N. Note that we are claiming that these numbers completely describe the object which exists beyond the coordinate system, so that when you rotate your coordinate system to a new one, since you already have complete knowledge of the object from the capital N numbers, you should be able to figure out what the new bunch of capital N numbers will be. That is, A1 prime, A2 prime up to AN prime are numbers which you can calculate starting from A1, A2 up to AN. Of course, a rule which tells you what the final result is going to be will depend on what particular rotation you are carrying out. And this rule, let's call that T1. So T1 is a map which takes A1, A2, AN, the initial values of the components, and maps them to A1 prime, A2 prime up to AN prime, the final values. That is the values after the rotation R1. Let us then carry out the R2 rotation to take us to our final coordinate system. Now for that, again, the same argument works, and we should be able to find out a map T2 which takes you from A1 prime, A2 prime, AN prime to A1 double prime, A2 double prime, AN double prime. Now comes the crux of our argument. As we have seen before, instead of carrying out the rotation in two steps like this, we could have carried out a single rotation R3, which is actually equal to the product R2, R1, which would have taken you from XYZ to X double prime, Y double prime, Z double prime. And once again, the fact that the objects that I am trying to describe exist beyond the coordinate system tells us that the numbers which describe this object may depend on a coordinate system, but should not depend on how the coordinate system got there. In other words, carrying out a single transformation, T3, corresponding to this rotation R3, would give you exactly the same result as carrying out these two transformations, T1 and T2, in succession. So T2, T1, which is the composition of the two transformations, T1 done first, then T2 being carried out, has to be the same as T3. Put more mathematically, what we demand is corresponding to every R there is a T. So there is really a map between the R's which describe how the coordinates transform and the T's which describe how the components describing my object transform. So let us call this map simply T. So the T for R1 is my T1, T for R2 is T2, and T for R3 is T3. Notice that TR3 has to be equal to TR2, TR1 according to our demand, and this translates to this property for our map. T, when fed the argument R2, R1, must give you the product or the composition TR2 times TR1. This mathematical statement happens to embody our demand that whether we get to our coordinate system in one go by carrying out a single rotation R2, R1, or whether we go there in two steps should not make any difference to our final values, the numbers which we use to describe our physical object in the final coordinate system. While this is a very, very simple demand, it actually has far-reaching consequences. In fact, we just saw a while ago that if we demand that this T of R is just a single number, then the only possible way that this can be consistent with the property of rotations is that this has to be 1. In other words, the only single component objects that we have are scalars. Indeed, this apparently very simple relation puts very severe restrictions on the possible forms of transformation rules, which is why we only end up with certain kinds of objects that we can see or use in physics and not other kinds of objects. Mathematically speaking, this has a special name. This is actually a group homomorphism between the group of rotations and the group of linear operators acting on the numbers which describe my physical object. Indeed, a major result in group theory, and one of the reasons why group theory is so important in physics, is that it tells us what kind of objects, what kind of transformation rules are possible for different kinds of operations, not just rotations. Now, we will not discuss group theory in any great detail here, but let me just point out that much of what we are going to say and much beyond what we are going to say would have been rather easy to state and describe had we approached this from a group theoretical angle. This equation is, after all, nothing but a mathematical version of our demand that whether we go to our final coordinate system in one go by carrying out the rotation R2, R1, or whether we do it in two steps, first R1, then R2, the final values for the components that we measure in our coordinate system should not depend on this. So, numbers can very well depend on coordinate systems, as we have stressed before, but should not depend on how you got to that coordinate system. So that's all that we are really claiming here. Now, if we borrow some language from group theory, which is actually the underlying theory here, this particular demand actually tells us that T is a map which preserves the group structure, the product structure of these operations that we carry out on our coordinates, the rotations. In other words, whether you compose the rotations first and then map using T, or whether you map the rotations first using T and then compose, you get the same result. In technical terms, what we have is what is called a homomorphism between the group of rotations and these transformations which act on our object. In particular, we are going to focus on linear transformations because they have many nice, interesting properties That is, we will demand T of R1, T of R2, T of R3 to act linearly on their inputs. And in that case, what we are going to end up with is what in group theory is called a linear representation of the underlying group, in this case, the rotation. Now, we are not going to actually use the full language of group theory here, simply because that would take us way too long to develop. But if any of you know enough group theory already, it should be very easy for you to figure out that all we are talking about are the various kinds of possible representations under rotation group. In fact, the vectors, tensors, and other objects that we see are nothing but different kinds of representations. Indeed, group theory would be a wonderful tool to have under your belt if you wanted to see what happens not only under rotations but under other kinds of transformations as well. And that is one of the reasons why group theory is so very important for physicists. For the time being, we are not going to use the group theoretical language here. But even without using the full power of group theory, we can draw some conclusions rather immediately from this particular demand that we have. TR2R1 is TR2 times TR1. For example, as we have already stressed, in 1D, that is, if we are talking about single component objects, T must just be a number, and then, as we have already seen, the one number which is consistent with this demand is T of R for every rotation is just 1. This is exactly what we call the scalar transformation rule. So there are objects which transform according to this, and these are what we call scalars. Now, a moment's thought would tell you that there actually is another rather obvious possibility here. Another obvious map, which is T of R is nothing but the determinant of R. Notice that what we want here is TR2 R1 is TR2 TR1, and determinant of R2 R1 from an elementary property of matrices is determinant R2 times determinant R1. So TR equal det R definitely satisfies our basic demand. So it seems that the statement that we made a while ago, scalars are the only possibility, is not really right. You do have another possibility right here. Well, actually you have infinitely many possibilities, because instead of det R, you could just as well have used det R to the power m, where m is any integer whatsoever, and this would still work. However, let me point out that if you are sticking to rotations and rotations alone, determinant of R is simply 1. So these infinitely many different possibilities that we are talking about are actually not different possibilities at all. All of them really tell you that TR is 1. So under rotations, these do not give you any new possibilities. And that's a good thing, because we have already proven that under rotations you can have only TR equal to 1. But what if we went away from rotations? Let's say we talked about general orthogonal transformations, which included rotations and reflections. Well, there, rotations would have determinant of +1, but reflections or combinations of reflections with rotations would have determinant -1. So we could have a special kind of object. T of R is +1 for rotations, but -1 when there is a reflection involved. In other words, the underlying object will be multiplied by 1 when you rotate your coordinate system, that is, will not change, but will be multiplied by -1 when you reflect. Now, such objects definitely do exist. They are precisely what we call pseudoscalers. Things which exactly behave like scalars under rotations, but behave oppositely to scalars under reflections. Scalars do not change no matter whether you rotate or reflect. Pseudoscalars do not change when you rotate, change sign when you reflect. Of course, you may have figured out that the integer m is not really very important here, because for an orthogonal transformation, the only possibility that you have is is data r equal to plus 1 or data r equal to minus 1. So for an even m, this would simply mean plus 1 always, that is a scalar. For any odd m, it simply means the same thing as data r. So under orthogonal transformations, general orthogonal transformations, that is, if you go beyond rotations, you do have a new kind of object, the pseudoscalar, but nothing other than that. As you must have realized by now, things get even more varied if we move away from orthogonal transformations and talk about general linear transformations. Because there, determinant of r might very well no longer be either plus 1 or minus 1, but could take some other value. And then you would be forced to ask the question, do we have objects which have data r to the power m as part of the transformation rule? The answer is, you do have such objects, and one particular such object is actually pretty well known, something which you are all familiar with. Just think of this a bit. Consider the density of any physical quantity, any scalar, like say the mass or the charge. Let's just focus on mass for the time being. It's mass by the volume. When you carry out a general coordinate transformation, what happens to rho? Well, you might be tempted to say density does not change, but that would not quite be right. What does not change is the mass. Rho prime in the new coordinate system must be m prime by v prime. The mass, being a scalar, does not change, but v prime, the new volume, is not the same as the old volume, is the determinant of the coordinate transformation matrix times the volume. That, after all, is exactly what the determinant means. It's a factor by which volumes get multiplied when you carry out a coordinate transformation. Of course, if we are talking of rotations, that data r would have been 1. But for a general linear transformation, data r would not have been 1. And then you end up with rho prime equals 1 by data r times rho. So all densities, mass densities, charge densities, all scalar densities, essentially conform to this rule, T of r is data r to the power m with m equal to minus 1. Indeed, you use a general term density whenever the transformation rule has an extra data r or some power of data r in the transformation, and that integer m that is sitting there is essentially what you call a weight. So we have met things which are beyond scalars and vectors and tensors right now. We have met scalar densities. Not really something new. You have known them all your life. But if you think of transforming a coordinate system, they actually transform in a rather different way from scalars. The only reason why you did not know this, perhaps, till now, is because you focused entirely on rotation of coordinates, and under rotation of coordinates, there is no way you can distinguish scalar densities from scalars. I'm pretty sure most of you thought of charge density or mass density as a scalar quantity. And you would be right, they are scalars under rotations, but they are not scalars under general coordinate transformations. Let us skip over the question about two-dimensional objects for the time being and go on to 3D objects. For 3D objects, if we are talking of linear transformations, the T of R should be a 3x3 matrix which acts on my 3-component column vector describing the object. So what we want are 3x3 matrices T1, T2, T3 corresponding to R1, R2, R3, which obeys T1, T2 equals T3 whenever R1, R2 equals R3. Now there is one very obvious choice here, and that obvious choice is nothing other than the trivial one. T of R is nothing but R itself. Remember, T of R here is a 3x3 matrix, so is R, and all we are claiming is that this demand that T1, T2 equals T3 whenever R1, R2 equals R3 can be satisfied rather trivially by just taking T of R to be the same as R. So we expect there to be objects which can be described by 3 numbers, and the numbers will transform when you carry out a coordinate transformation exactly the same way that the coordinates do. because T of R, the matrix which describes this transformation, is the same as the coordinate transformation matrix R. Is this a surprise? Of course not, because this is nothing but what we have been calling vectors. The vector transformation rule exists because it is consistent with our basic demand that ultimately the transformation rule has to satisfy T of R1 R2 is T of R1 times T of R2, and T of R equals R definitely satisfies that. Well, in addition to that, you can easily see that det R times R would definitely satisfy our basic demand as well. And once again, we can point out that if we are only interested in rotations, this would be nothing new because det R is 1, so T of R is always equal to R. But if we go beyond rotations and talk about orthogonal transformations in general, then we have this situation that for rotations, T of R will be the same as R if this rule were followed. But for reflections, T of R would actually be minus R. So we will have a new kind of three-component object, that is new compared to what we have just seen, described by three numbers which transform exactly the same way as coordinates do under rotations, but exactly the opposite way as the coordinates do when you reflect. So you get an extra minus sign from the determinant. Most of you already know what we are talking about here. These are the objects which are called pseudovectors or axial vectors. If your concern is with rotations only, then you cannot distinguish pseudovectors from vectors at all. But when you are concerned with other orthogonal transformations as well, pseudovectors behave differently from vectors. They pick up an extra minus sign whenever there is a reflection involved. So not only have we explained why vectors exist in 3D, we have also explained why pseudovectors exist when we talk about transformations other than just rotations. If we talk about more general transformations, you could have other possibilities as well. Sticking to 3D for the time being, let's just try out a few more possibilities. We have already seen that T of R equals R works fine, but what about T of R equals R transpose? That, after all, is a 3x3 matrix as well, so why not try that? Or perhaps T of R equals R inverse. All coordinate transformation matrices are invertible matrices, so R inverse does exist, and that's a 3x3 matrix, so why can't we use this? Now let's see whether we can use either this or this. Well, remember our basic demand. T of R1, R2 has to be TR1, TR2. Now T of R1, R2, if T of R were RT, would be R1, R2's transpose. And that, as we all know, is R2 transpose R1 transpose. And that is equal to T of R2 times T of R1. Note that we do not have our demand. Our demand was T of R1, R2 is T of R1 times T of R2. What we have here is that these two things have been switched. So this choice doesn't work. You cannot use the transpose of R for the transformation matrix for a three-component object. Can you use R inverse? Well, you should be able to guess by now that the answer is no, because R1, R2 inverse has the same property and hence the same problem, that the order reverses. When you want to undo the result of two successive operations, you have to undo the last one first, and the first one you did has to be undone last. And this again gives you TR2 times TR1, again not what we want. Well, now that we have met with two failures, why don't we just try combining the two failures into one transformation rule? What about T of R is R transpose inverse? Well, given the fact that both of our earlier attempts failed because of a reversal of order, it might very well seem reasonable to expect that this will actually work, because two reversals will get you back to what you wanted. So let's see whether that really works for this particular rule. TR1R2 is R1R2's transpose inverted. That is, of course, R2 transpose R1 transposes inverse, and that is R1 transposes inverse times R2 transposes inverse, and that really is T of R1 times T of R2. So while we cannot really have three component objects which transform by R transpose acting on them or R inverse acting on them, remember here we are talking of these objects as three component column vectors, and the transformation acts on them from the left. So R transpose or R inverse are not allowed transformation matrices here, but R transpose inverse is. So we do have three component objects for which the transformation rule will be A, which is now a three component column vector, changes to R transpose inverse A. Now, for those of you who have listened to the earlier lectures, this should be a very familiar thing. This is exactly what we call a covector transformation rule. And why did not we talk about covectors in our early exposures to the subject? The answer is, if we are sticking to rotations and rotations alone, the matrix R would be an orthogonal matrix. So R transposes inverse would be the same as R. So no distinction from vectors under orthogonal transformations. Not only rotations but reflections as well. So under orthogonal transformations, covectors and vectors behave exactly the same way. And if orthogonal transformations, rotations and reflections are all you were ever interested in, then you would not be able to distinguish a covector from a vector. However, when you move away from orthogonal transformations, covectors come into their own right as an object of interest. In particular, when we go to the four-dimensional world and talk about events whose coordinates are given by not just x, y, z, but also the time, which we write as ct and or x0, we end up with a non-orthogonal transformation when we go to another inertial observer, the so-called Lorentz transformation. And there, we have to distinguish between two kinds of four-component objects. Ones which transform like the coordinates, that is, vectors or four vectors, and ones which do not transform like the coordinates but transform according to this rule, R transpose inverse. Those would be the four covectors. And as we have already seen in previous lectures, covectors are a very, very important part of the whole theory. What I would like to emphasize here is just from the demand that T of R1, R2 has to be TR1 times TR2, we can also understand why covectors exist and when they exist. In other words, why they don't show up when we talk about rotations. Let's move on now to tensors of rank 2. Let us use our familiar moment of inertia tensor, the example that we talked about in detail in the last lecture, as the one example that we are going to talk about. This is an object with two indices, and when you transform your coordinate system, it picks up two rotation coefficient matrices, Rik, Rjl, IKL. Now my claim is that this particular transformation rule that you have is perfectly consistent with our TR1R2 equals TR1 TR2 demand. In order to see that, let me first take an easy way out. Let us try to think of this as a matrix relation. In fact, in the last lecture we talked about the matrix I, not the identity matrix, but the moment of inertia tensor matrix, made out of I11, I12, I13 and so on. which under a coordinate transformation transforms by a similarity transformation. I prime is Ri, R inverse. In the last lecture, we discussed why this rule, when written in component form, is exactly equal to this rule, the so-called standard rule for transformation of two second rank tensors. Now, let us try to see what happens to I when you carry out two successive rotations. So you are starting with the moment of inertia tensor written in the matrix form, I. Then you carry out a rotation R1 of coordinates. So I now becomes R1, I, R1 inverse according to our standard rule here. After that, we carry out a further rotation R2. Now, what happens is, this matrix I prime, that gets changed to R2, I prime, R2 inverse. And this is our final I double prime, the final form of the moment of inertia tensor in the final coordinate system. But now let us take a look at what I double prime is using what we know from matrix theory. I double prime is R2, I prime R2 inverse, but I prime is R1, I, R1 inverse. So what we have, using the fact that matrix multiplication is associative, is that this is given by R2, R1, I, R1 inverse, R2 inverse. And therefore, it is the same as R2, R1, I, R2, R1's inverse. So if you carry out a transformation using R1 first and then using R2, you end up with a transformation which you would get using R2, R1, the product rotation matrix, in one go. So at least in this indirect version, it's easy to see that the transformation rule actually obeys T of R2, R1 is T of R2 times T of R1. Now, why did I call this proof indirect? I did not mean that it was an inferior proof or anything. All I meant was, despite the fact that the new components of I prime are related to the old components in a perfectly linear fashion, as you can see on the top of your screen right now, we did not actually use this linear map directly. We used, on the other hand, the action of this similarity transformation on a matrix I to figure out that the action of R2, R1 is the same as the action of R1 first and then R2 acting on the result. But we can also show this more directly by writing down the relationship I prime ij equal to Rik Rjl Ikl in the form of a matrix T acting on a column vector which has all the I elements. So firstly, let us think about the column vector which contains all the I elements. Since there are 9 elements in I, this will be a 9 by 1 column vector. Basically, I will be rewriting the matrix I11, I12, I13, as you can see here, in this particular form. I11, I12, I13, I21, all the way down a column. Of course, this brings in nothing new, it's just a different way of writing the same thing. Now, how do these elements transform? Of course, the transformation rule is right here. I prime ij is Rik Rjl Ikl. So just as an illustration, let's look at I prime 1, 1. This will of course be something which this formula yields when I and j are both fixed at 1 and 1 and k and l are summed over all possible values. So you get R11, R11, I11. This of course is the k equal to 1, l equal to 1 term. Then you have the k equal to 1, l equal to term, 2 term here, which is R11, R12, I12, all the way down to R13, R13, I33. That's the k equal to l equal to 3 term. There are 9 terms in all of them added up together. So of course, as you can see, I prime 1, 1 really is a linear combination of all these elements with coefficients R11, R11 for I11, R11, R12 for I12, and so on. So it is pretty easy to write down the 9 by 9 matrix which actually acts on this 9 by 1 column vector to produce the new 9 by 1 column vector made out of I'11, I'12, and so on. And that is what is written here. Since the 9 by 9 matrix is a big bother to write down, I have not bothered to write down all its terms. R11, 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 R12, this is of course the first row. This is from the expansion of I'11 which you just saw. If you wrote down I'12, you will see that comes out to be R11, R21 times I11. That's the k equal to L equal to 1 term. I and j are fixed at 1 and 2 for this. Then you have R11, R22, I12, and so on. And that is exactly what this row of the matrix will give you when you multiply by this column vector. So basically you have a 9 by 9 matrix. And what is important is both for the column vector and for the matrix, we do not use 9 distinct numbers as indices. Instead, we use index pairs 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. These 9 pairs are actually the 9 indices here. So, we are going to use double indices or pairs of indices to stand for a single index of the column vector, as well as 2 such pairs of indices to talk about an element of the transformation matrix T. So TR's ijkth element, as you can easily see from the example, must be Rik Rjl. This of course is a consequence of the general transformation rule. You would recognize that this is nothing but the statement that the matrix T is a direct product of the matrix R with the matrix R. So 2 R matrices, 2 transformation matrices for coordinates. You take the direct product of them, you get a 9 by 9 matrix, which is the matrix of transformation for the second rank tensor. And just to show that T of R actually obeys our basic property, let's look at TR1, TR2's ij klth element. Once again, let me emphasize that here the pair ij stands for the row index and the pair kl stands for the column index. Now, by definition, this is equal to, by the definition of matrix multiplication, this is equal to TR1 ij pq times TR2 pq kl summed up over all possible values of p and q. And we can simply directly write down TR1 and TR2 in the basic form starting from TR ijkl is Rik Rjl. TR1 ij pq becomes R1 ip R1 jq. TR2 pq kl becomes R2 pk R2 kl. Now notice that we have a sum over p and a sum over q, and they take all their possible values. But it is very easy to see that these two sums can be decomposed into 2 separate sums. That is, you have a sum over p of R1 ip, the very first term there, and the other term which contains p, that's R2 pk. Similarly, the sum over q essentially sums up R1 jq times R2 ql. And now again, using standard rules of matrix multiplication, we end up with the first term being R1 R2's ikth element and the second sum being R1 R2's jlth element. And this of course is nothing but T R1 R2's ij, kl element. And this verifies for us that TR1 TR2 for this transformation rule is actually TR1 R2. By the way, this detailed proof that I gave you just now could have been omitted by any of you who is familiar with direct products and how to multiply direct products of matrices. Then this would be a trivial rule, because basically you have this rule for direct product of matrices: A cross B times C cross D is essentially AC times BD. This thing is of course true for all matrices for which the multiplication is compatible. In our case, what you have is basically R1 direct product R1 for TR1, and you're multiplying that by R2 direct product R2, and using this basic property of direct product matrices, you end up with R1 R2 direct product with R1 R2, and that of course is T of R1 R2. In fact, the proof that I gave you using the indices right now is essentially the same as the proof of the result that A cross B times C cross D is AC cross BD. We have just used that in our specific context here. This generalizes rather trivially, though slightly cumbersomely, for the case of a general P, Q tensor. For a P, Q tensor, the transformation rule has P coefficients which come from the coordinate transformation and Q other coefficients which come from covector transformation coefficients. And basically the matrix capital T for a given transformation S essentially is the direct product of P such vector transformation matrices and Q covector transformation matrices. And once again, just by using the standard property of the direct product, it can be easily shown that T of S1, S2 here will be TS1 times TS2 as well. So, a general tensor also satisfies our basic demand that whether you change your coordinates in one shot or whether you do it in steps should not affect the numbers that you use to describe your tensor or any object in the final stage. So once you have convinced yourselves that the PQ tensor has a transformation rule which actually obeys our basic guiding principle, it should be pretty easy to go over from the PQ tensor to the PQ tensor density with weight W. After all that does is that there is an additional factor of determinant of S to the power W, where S is the coordinate transformation matrix. And since det S1 times det S2 is det S1 S2, it is easy to see that the incorporation of this extra factor will not change the fact that our basic general demand of TS1 S2 is TS1 TS2 is being obeyed. Basically, what we have done here is try to see why vector transformation rules are the way they are. Transformation rules have to exist because you have objects which can be completely described using a bunch of numbers, and once this complete description is available, you should be able to describe that equally well in another coordinate frame, as we have been saying in all of these lectures so far. But these transformation rules cannot be completely arbitrary. They have to obey this very basic restriction. In a fancy language, I could say that these geometrical objects that we are dealing with, vectors, covectors, tensors and so on, all furnish linear representations of the underlying transformation group for the coordinates. But all that really means is just this: whether you do it in 2 steps or 1 step, the result of a coordinate transformation will always be the same. Okay, so far we have understood the fact that the transformation rules for vectors, tensors, etc. do satisfy our demand. But are these the only quantities that satisfy our demand? Now, a detailed answer to this question is rather involved, especially because it depends crucially on the kind of transformations you are talking about. If we confine ourselves to coordinate rotations only in 3 dimensions, then a much more definitive answer can be given. But even there, giving the full proof of what I'm going to say is not really feasible here. Firstly, because it would take too long to describe, and secondly, because it would involve techniques which we are not really going to need in the rest of this series of lectures. As I have been saying, a group theoretical treatment of the rotation group would actually tell you all its possible representations, and that will tell you what kind of objects can really exist. Those of you who have studied advanced quantum mechanics would be familiar with what I am talking about here, although you may not have perhaps heard of this in this particular language. Indeed, the theory of angular momentum representations, the familiar J, M states from quantum mechanics, is essentially the theory of representations of the rotation group. So, many of you can pick up the details of this from your quantum mechanics text. But let me just give you the answer here without trying to give any detailed proofs. It so happens that the rotation group has representations, or rather irreducible representations, for every dimension. An irreducible representation is simply one which is not built up by putting together smaller representations. Remember the question I raised at the very beginning of this lecture. Do you know of any two-component objects in classical physics? As I said there, you could have very well said two scalars, but that would be putting together two smaller representations to build up a bigger one. That's not the kind of object we are talking about. A quick answer would be, you do have two-component objects which transform non-trivially under rotation group and which is not built up out of smaller pieces. However, I am pretty sure none of you can come up with an example of a genuinely two-component object in classical physics, simply because there aren't any. If you followed the standard techniques that people learn in angular momentum algebra in quantum mechanics and tried to build up a two-dimensional representation, you would find a representation. But that particular bunch of transformation matrices will have one rather unfortunate property. And that is, if you were to rotate your coordinates through an angle of 2 pi, the transformation matrix corresponding to that would not be the identity matrix, but would rather be minus identity. Now, since rotating a coordinate system through 2 pi actually brings you back to your original coordinates, it's obvious that physics should not be affected by a rotation through 2 pi. And so, we would have expected the transformation matrix to become the identity matrix in this case. As I said, it actually turns out that it is negative of the identity matrix. By the way, anybody who has studied spin half-part objects in quantum mechanics knows about this. And that is exactly where you see such objects, not in classical physics, but in quantum mechanics. In classical physics, such objects can't exist because the numbers that you see in classical physics, the components of your object, are directly measurable quantities. If they were to change sign, you would be able to distinguish a 2 pi rotation physically from a zero rotation. On the other hand, in quantum mechanics, it's really the modular square of the basic object, the wave function, which is used. So, if the wave function were to pick up an extra minus sign, which is exactly what a transformation matrix of minus the identity would do, has no physical consequence. Minus 1 mod square, of course, is plus 1. So, in the quantum world, you do have such objects. But in the classical world, you will find no such thing. In a sense, our series of lectures have come full circle with this one. When we started out, we talked about vectors in terms of their transformation properties, and then introduced covectors and tensors, again as a bunch of numbers or objects which can be described by a bunch of numbers which transform in a particular manner. Then, a few lectures ago, we came up with an entirely different way of looking at tensors, as multilinear maps which maps covectors and vectors into numbers. And there we showed that all that we had talked about earlier could be derived as simple consequences of this particular way of looking at tensors. Today's lecture has brought us back to coordinate transformations, but with a slight difference. Here we were really interested in a slightly deeper question. We were not asking how vectors and tensors transform. We had already answered that in previous lectures. We were actually asking, are they the only possibilities, or why do they exist? Of course, one of the basic questions that I raised at the very beginning, why should we bother about tensors, have not been answered here. But we will answer this question quite definitively in the lectures to come, especially when we talk about specific applications, like in special relativity or in general relativity. Let me stress once again, those lectures are not going to be special relativity or general relativity courses. You will not learn enough from them to be able to gain mastery on those subjects. We will just talk about the mathematical aspects of these objects as they are used in special and general relativity respectively. But before we even go there, in the next lecture, we will go back to our familiar three-dimensional vectors and talk about that in more concrete practical terms, talk about physical examples, many of which will be very familiar to all of you, and also discuss one object which we had not really touched upon earlier, that was more my omission, the nature of the cross product of two vectors. Exactly in what sense is that a vector? But for that, we will have to wait for the next lecture. Bye till then.